Hey, let's review what you know about polynomial functions. This chapter is about the algebraic functions with a particular focus on polynomial and rational functions. Well, notice if you have ax to the 0 power, which just reduces to a, remember that's giving you y equals a, which is a horizontal line. Horizontal lines are the simplest kind of polynomial function. They're called constant functions. If you have y equals mx plus b, that's a basic linear function, and those address lines that are either diagonal rising or falling. Then h of x, y equals ax squared plus bx plus c, you know is called a quadratic function. And this is the quadratic function written in its standard form. And you know those create parabolas that open up or down. And then k of x, you know, is a cubic function. And you know cubic functions either go 1, 2, 3 or 1, 2, 3 because the degree tells you what the graph is going to be shaped like. J of x, since it's to the 4th power, is called a quartic function. So I'm going to have to count to 4 in my graph. It'll be something like 1, 2, 3, 4 and 1, 2, 3, 4. All of these, I'm giving you the most garden variety kind of polynomial function that we can. In calculus, you get into the ones that maybe are a little bit different when you have more tools for analysis at that point. L of x, with it being a polynomial function of 5th degree, is called a quintic function. So I'm going to count 1, 2, 3, 4, 5. Or it might go 1, 2, 3, 4, 5. And then m of x is a 6th degree polynomial function. At this point, we don't have special nouns anymore. So we'll just have 6th degree polynomial functions, 7th degree polynomial functions, and so forth and so on. So that p of x, I'll in general call an nth degree polynomial function. And I'm going to abbreviate polyfunction like that. So a 6th degree polynomial function, you know, is going to take 6 directions on the graph. So something like 1, 2, 3, 4, 5, 6. Or maybe 1, 2, 3, 4, 5, 6. And an nth degree polynomial function will take on n directions in general in your most basic form. Now I have the large smiley face by h of x because today's focus is a review on quadratic functions. So notice that all the functions I'm showing here are quadratic functions that are in vertex form. So I know how to graph these. I know that f of x is your most basic quadratic with a vertex at 0, 0, and a value of 1, so it's out 1, up 1. I know g of x is simply a vertical reflection, so instead of going out 1, up 1, I'm going to go out 1, down 1. I know h of x also has its vertex at 0, 0, but it's been vertically stretched. So instead of going out 1, up 1, you go out 1, up 3, because I've got to triple the vertical distance while maintaining the horizontal. So this is a vertical stretch. It makes it taller, and it may appear skinnier, but it's really taller. Now, k of x has been shifted vertically up 2, but the a value is 1, so it's still out 1, up 1. Now, before I switch slides, I'm always going to ask you to name the vertex and the intercepts on each of these. So if I shift and say, okay, well, let's name vertex. Vertex is really, really easy on all of these. If the parabola is in vertex form, the vertex, of course, is just immediate and obvious, which is nice. So the first 3 have a vertex of 0, 0, while k of x, since I shifted it up 2, now has a vertex of 0, 2. I'm also going to ask you to find the x and y intercepts, let's start with the x-intercepts first. Well, there's no work necessary on the first three, because if the parabola has its vertex on the x-axis, and a lot of times I'll say if the parabola sits on or hangs from the x-axis, then its vertex and its x-intercepts are the same. So I could say x equals 0 is a double root here on all of these. Now, I don't need to do work on this fourth one either, because I see with the parabola hovering above the x-axis and opening up, it never touches or crosses the x-axis. So I'm not going to do work to find that. I'm going to say none. Now, if you did do the work, you would set x squared plus 2 equal to 0. You get x squared equals negative 2. And when you take x equals plus or minus the square root of negative 2, which is imaginary, answers for x tell you that there's no roots. But I say, why do the work when, if you've already sketched it, you know that already. So now let's move into the y-intercept. And again, the y-intercept is just the point 0, 0 on these first three, because the y-intercept and the vertex are one and the same. And on the last one, the y-intercept and the vertex are also the same, since the vertex is still on the y-axis. So if all you do is move a parabola up or down, its y-intercept is going to match its vertex. So let's do three more that are in vertex form. Let's start by sketching each of these the same way. So on j of x, do you see the x plus 4 means it's been moved 1, 2, 3, left 4. Its a value is 1, so from the vertex it's still out 1, up 1. From L of x, do you see right 1, down 3? So right 1, down 3 is here. Do you see that the negative here makes it open down, but it's only an a value of 1/4. So I could go out 1, down 1/4, but that's not very good. Okay? Normally I go out 2, down 4, because 2 squared is 4. Oh, now I could do that, because from the vertex, if I go out 2, down 1/4 of 4 would be down 1. So again, from the vertex, I could say out 2, down 1, and those are better points to plot. It gives me a more accurate read on my parabola. And then m of x only moves left 5, down 6. So 1, 2, 3, 4, 5, down 1, 2, 3, 4, 5, 6. And the a value is 2. So instead of going out 1, up 1, I'm going to double that vertical stretch and go out 1, up 2. So again, vertex form is great for naming the vertex. There's no work. We really like vertex form. So I can see that I put the vertex at negative 4, 0. On this one, I can see that I put the vertex at 1, negative 3. And on the third one, I put the vertex at negative 5, I believe negative 6. So let's go into the x-intercepts, because we always want vertex and intercepts. So on this one, I don't need to do any work. Since the vertex sits on the x-axis, x equals negative 4 is your double root. So technically negative 4, 0 is your double root, but we'll go to x's at this point for the rest of this chapter. Now on this one, since the parabola turns upside down and hovers below the x-axis, I can see there are no roots. So no need to go through the work and get imaginary. I can see that there are no roots. Save yourself some algebra time. On the x-intercept on this one, I can see that the graph will cross the x-axis, but I can't tell exactly where because my graph is not that precise. So I'm going to take the equation and set it equal to 0. I need to first isolate x plus 5 squared, and I do that by adding 6 and dividing by 2. So I get 3. Now I'm going to take the square root of both sides, so x plus 5 equals plus or minus the square root of 3. X equals negative 5 plus or minus the square root of 3. So if you think about it, the square root of 3 is about 1 point something. So negative 5 minus 1 point something would be negative 6 point something. 1, 2, 3, 4, 5, 6 point something. So it's somewhere between negative 6 and 7, and your graph doesn't have to be more accurate than that, so I could kind of add on if I wanted to. I can see that it makes sense algebraically and graphically. They fit together. Then negative 5 plus 1 point something would be negative 3 point something. So 1, 2, 3 point something, somewhere between negative 3 and negative 4. And again, I can see that that's reasonable. Even though my graph is imperfect, I can see that's reasonable. Now, we're going to switch gears. Before we do, how about you do a little practice work?